So lattice enthalpy, as mentioned yesterday when we went through the definitions, is the enthalpy change when 1 mole of ionic solid is either formed from gaseous ions or is broken down into gaseous ions. We use the same term, lattice enthalpy, for both one being positive, one being negative, and them being equally opposite. But what does it actually really mean? So if we consider that our lattice enthalpy of formation, we've got our sodium ions, and they're in the gaseous state, and we've got some chloride ions in the gaseous state, and we're going to make them into 1 mole of ionic solid. Now, the enthalpy change, the energy that's involved in going from being gaseous ions to being the ionic solid, is a measure of how strong the ionic bond is. So you would expect different ionic solids to have different values for their enthalpy change, and if we can see the different values of lattice enthalpy, then we get a good idea of how strong those ionic bonds are. Now, if we think about this in terms of energy levels, so I'm just going to put energy, okay, then it would make sense that our gaseous ions in this this is the highest energy we can be. This is ionic, so we've got ions and they're so far apart in a gas that there's no ionic interaction, so there's no electrostatic attraction between the sodiums and the chlorides because the ions are far apart. So this is going to be a pretty high energy state. So we're going to draw this one up here, and this is where we've got our Na plus and our Cl minus in gas form. And it would make sense that our ionic solid, sodium chloride, that sits in the salt cellar on the side in the kitchen and that you sprinkle on your dinner, is a fairly low energy form. It's very stable. So this is going to be much lower in energy than our sodium ions and our chloride ions. So it therefore would make sense that, so this distance between them, if we've got an arrow going up, we have a positive enthalpy change, and this would represent our sodium chloride breaking down into the sodium ions and the chloride ions. So we're going to have to put lots of energy in. This is endothermic. And if I were to have the arrow going in the other direction, we're going from our positively charged ions and our negatively charged ions that are in a gas state and they're coming down in energy, we're going to have a negative enthalpy change, and it's going to be exothermic. So if lattice enthalpy is a measure of the strength of the ionic bonds and the ionic bonding, then it would make sense that different things can affect the size of the lattice enthalpy. So there's 2 main factors that come into play here. The first one is the size of the charge, so the charge on the ions. Okay, and the second one would be the size of the ions. So the charge on the ions is going to have an effect. You would expect a +2 charge and a -2 charge to be much more strongly attracted to each other, so you're going to expect them to have a higher degree of ionic bonding, so a bigger lattice enthalpy. And the size of the ions is also going to have an effect. So a really small ion is going to be able to get much closer to the oppositely charged ion. So a small positive ion is going to be able to get closer to a small negative ion than a big ion, then big ions are going to be able to get to each other. So that's also going to affect the size of this ionic bond and the strength, and therefore the lattice enthalpy. So if we consider something like magnesium oxide, which is 2 plus and 2 minus, and quite small ions, this is actually going to have a much greater magnitude of lattice enthalpy than it would be for sodium chloride, which is only 1 plus and 1 minus. Now the problem is we want to be able to work out lattice enthalpy because it gives us an indication of the strength of the ionic bond, but it's impossible to measure it experimentally and to actually directly measure it. So we need to use some form of Hess cycle to measure it indirectly. Now we can't use the little Hess cycles that we learnt in energetics because they're just not complicated enough to fit in all the information because there's several changes to take place. But we can use the same idea that doesn't matter which route we take, whether we take the direct route or the indirect route, so long as the states are the set and the conditions are the same at the start and the end, then the overall energy change will be the same. So what I've done to start off constructing my Born-Haber cycle, which is the type of Hess cycle we use for doing this, we know that our sodium chloride is going to be the lowest energy state. So our solid, our ionic solid, goes at the bottom, on the very bottom line. And I know that the gaseous ions of sodium ions and chloride ions, this is what I'm going to try and find out, is the energy gap between them. So this is our lattice enthalpy that I'm trying to find out. So now we need to fill in other states that we think we might be able to measure. So something I might be able to measure would be the enthalpy of formation of sodium chloride, actually practically from sodium metal and chlorine gas. Now, I know that sodium solid and chlorine gas are going to be at a higher energy level than sodium chloride ionic solid. So this arrow between the sodium and chlorine would represent our enthalpy of formation, so delta FH. So if we know what the enthalpy of formation is, and if they gave us a value for it, we would be able to know that little part. So what follows next is a series of all the little steps that need to be taken to get from our elemental states of sodium as a solid and our half a chlorine gas, going from there to this imaginary state of sodium ions and chloride ions that are not attracted to each other because they're far and spaced apart. So the first step in doing this would be to take our sodium solid and turn it into sodium gas. So I'm going to write on here to Na gas and plus a half Cl2 gas. And this is the enthalpy. I'll use a red arrow this time. This is our enthalpy of atomization of the sodium. Now, our next mini step is going to be taking that sodium that's now a gaseous atom and turning it into a sodium gaseous ion. So I now want this to be Na plus gaseous plus a half Cl2. Okay, and this would be represented by another arrow going up. This would be our ionization energy. Our ionization enthalpy for sodium. Now all of these values would be given to you in an exam question, and you would just need to be able to construct the Born-Haber cycle and make sense of those values and add them up in the cycle. So at this point we can see our sodium ion is in gaseous form, it's ready, but we now need to start working on our half a chlorine molecule. So before I can turn my half a chlorine molecule into a chloride ion, the first thing I need to do is atomize it and turn it into a chlorine atom. So we're going to go up to the top level now, and we're going to have our sodium ion as a gas, and we're going to have a chlorine atom as a gas. Okay, and we've still got our little electron hanging around that we had from before, from when the sodium lost it. And we call this is our delta, this is our atomization of the chlorine. Okay, ideally, I would be writing on next to these little symbols, I would be putting Cl or Na to say what they're for, but I'm kind of out of space. Okay, so our final step then, we've got our sodium ion and our chlorine atom and our electron, but we now need to come back down in energy, down to our sodium ion and our chloride ion. Now this is because chlorine quite happily gains one electron to become a negatively charged ion. So we're going to use green because we're coming down. And this represents our enthalpy of electron affinity. So this is delta EA H. And now we've reached the point where we've got our sodium ions and our chloride ions. And so we would then, by adding up all of our different values going up and taking away our value going down, the difference between them is going to give us this value. I'm going to put an arrow on both ways because this is our lattice enthalpy. Okay, and it can either be our lattice enthalpy of dissociation, which would be where it would be breaking up, or it can be our lattice enthalpy of formation, where the ions are forming, depending on whether we give it a positive or a negative charge, depending on which version they ask you to calculate in the exam. Now you'll see I've put on all the values for the different enthalpy changes going around the cycle. So we can show how the lattice enthalpy is worked out by just adding up everything on one side and taking away the coming back down the other side. So we can see that our 411 and the 107 and the 495 and the 121 add up to 1,135. If I take away the 349, then I'm left with 786, and that's kilojoules per mole. Now you do need to remember that if that is lattice enthalpy of formation, it's going to be negative. So it'll be minus 786, but if it's lattice enthalpy of dissociation, then it's going to be positive. So it's going to be plus 786. Okay, that's enough for now on Born-Haber cycles. So I've got one final point on Born-Haber cycles, and that's this idea of theoretical values versus experimental values. Now, it might surprise you to know, but the values we've been looking at, so from Born-Haber cycles, these are experimental values. So these come from the Born-Haber cycles. Now, you don't have to be aware of how to make them or do the calculations, but you do need to be aware that physicists are able to use mathematical modelling to come up with theoretical values. So these are purely maths. So based on the idea of a pure ionic solid. So these are mathematical. And if the value that comes out from the experimental value from the Born-Haber cycle is really close to the mathematical value, then that tells you that your ionic solid is very much a pure ionic substance. But if there's deviation between the two, then it would suggest that your ions are distorted and that you have some covalent character to your ionic substance. So although it's overall ionic, it's made up of ions, there might be some distortion within that leads to it having covalent characteristics. And just to show you what I mean by that, if we consider sodium chloride, we just looked at on the previous page, has a experimental value that's derived from a Born-Haber cycle of 771 kilojoules per mole. And if you do a purely mathematical value based on Coulomb's law, then it comes out with a value of 766. So you can see they're actually quite close. There's not a very large amount of deviation, and that would suggest that both sodium ions and chloride ions are beautiful and spherical. So let's draw some nice spheres. So if we compare this to the same data for silver chloride, so AgCl, the experimental value that you'd obtain from a Born-Haber cycle for silver chloride would come out at 905. But the mathematical value, based on Coulomb's law, would be 770. Now, there's a massive difference, a much bigger deviation between those values, which suggests that we've got far more of a covalent character in this ionic lattice than there is in the sodium chloride. And that's because we've got some distortion of our shape. So let's draw on. We've still got, so this is our silver, but our chlorine is going to be a much more distorted shape as the negative cloud of the cloud around the negative ion gets distorted by the positively charged silver. Okay, have a go at all the questions on the sheets and I'll talk to you about them next week in the tutorial.